How large is the universe we can actually see? When astronomers talk about the scale of the universe, they are not speaking about imagination or speculation, but about light that has physically arrived at our instruments after traveling for immense stretches of time. Every faint point in the sky is a real signal, a stream of photons that left its source long ago and crossed expanding space to reach us. What we observe is not a distant object as it exists right now, but a preserved moment from the past, carried forward at a constant speed through a universe that has been changing the entire time. This question matters especially now, because the James Webb Space Telescope has begun receiving light that has traveled almost the entire history of the universe, allowing us to measure scale at depths that were previously unreachable. This channel exists to explore those moments slowly and clearly. And if this kind of quiet scientific curiosity feels right to you, you are warmly invited to like and subscribe. Our goal is to reach 1,000 subscribers by the end of January, and when we do, we will donate $100 to UNICEF, helping extend access to learning to those who cannot easily reach knowledge through the internet. And as you listen, you might take a moment to leave a comment sharing where in the world you are listening from, knowing that this same sky stretches above all of us. After that brief pause, the sky itself quietly takes the lead again. The idea of scale begins to settle not as something abstract, but as something physical and patient, something that arrives piece by piece. Light does not rush. It moves at a fixed speed, and while it travels, space itself continues to stretch. Galaxies drift farther apart. Wavelengths lengthen, and the universe subtly reshapes the message before it ever reaches us. This is the process the James Webb Space Telescope is designed to observe directly, by listening to light that has been stretched across nearly the entire age of the cosmos. Scale begins here, not with size, but with travel. Because of this, distance slowly blends into time. A nearby star is seen almost as it is now, while a distant galaxy is seen as it once was, long before planets like Earth even formed. The farther the light has traveled, the older the story it carries. Looking outward becomes an act of looking backward, not by imagination, but by physical necessity. This is why astronomers speak of depth rather than just distance, because the universe reveals itself in layers stacked by time. Layers that James Webb can now resolve with unprecedented clarity. As those layers accumulate, scale becomes something you can sense rather than calculate. Each deeper observation adds not just more space, but more history. Galaxies appear younger, smaller, less settled. Structures look incomplete, still assembling under gravity. The universe, at great distances, does not look finished, and that unfinished quality is itself a measurement, one that Webb's infrared vision makes visible rather than inferred. In this way, the scale of the universe is not a single number or boundary. It is a gradual unfolding, defined by how far light has been able to reach us since the beginning. The universe does not simply grow larger as our measurements improve. It grows deeper, revealing earlier chapters that were always present, waiting for instruments like James Webb to become sensitive enough to receive them. Scale becomes not something we impose on the universe, but something the universe quietly shows us, one traveling signal at a time. As the depth increases, something subtle happens to our sense of proportion. Nearby space feels familiar and orderly, with stars arranged in steady patterns and galaxies appearing as settled islands of light. But as observations extend farther, especially through James Webb's measurements, the universe begins to look less stable and less complete. Shapes grow irregular. Light becomes faint and stretched. The cosmos starts to reveal stages of growth rather than finished forms, and scale quietly shifts from being about size to being about development. This is because scale is inseparable from cosmic history. The universe has not always looked the way it does now. In its earliest eras, matter had only begun to gather, pulled together by gravity into the first rough structures. When we measure great distances, we are measuring how far back into that formative process we can still receive light, and James Webb allows us to observe those early stages directly rather than reconstruct them indirectly. The scale of the universe, in this sense, is a record of how much of its own past is still visible to us. There is also a natural limit built into this process. Light can only travel for as long as the universe has existed. No matter how powerful a telescope becomes, it cannot see beyond light that has not yet had time to arrive. This boundary is not a wall in space, but a horizon in time. It marks the farthest distance from which information has been able to reach us since the universe began expanding. When astronomers speak about the observable universe, this is what they mean, and James Webb now operates close to that horizon. Not everything that exists, but everything that has had enough time to be seen. That horizon gives scale a quiet precision. It tells us that the universe is not just large, but measurable, even if those measurements stretch the limits of intuition. The observable universe has a finite size, not because the universe ends there, but because light has a finite history. Scale emerges from this simple physical constraint, turning the universe into something that can be mapped layer by layer, rather than imagined all at once, especially now that James Webb can populate those layers with real structure. As observations push closer to that horizon, the nature of light itself becomes more important. Over immense distances, the expansion of space stretches light waves, shifting them toward longer wavelengths. Colors drift toward red, and eventually beyond what human eyes can see. This stretching is not a distortion or loss of information, but a signature of travel. It tells astronomers not only how far the light has come, but how much the universe has expanded during its journey, information that James Webb is uniquely equipped to capture. In this way, scale carries a rhythm. Light leaves a source, space expands, wavelengths stretch, and information arrives altered but intact. Each step adds context. Distance is no longer just separation, but participation in cosmic change. The farther light travels, the more the universe has evolved around it, and the more history becomes embedded in its signal, history that James Webb now gathers directly. What this reveals is that scale is dynamic. It is not fixed by rulers or coordinates, but shaped by motion, expansion, and time. The universe is not a static container, filled with objects at various distances. It is an active process, with space itself changing as light moves through it. Measuring scale means accounting for that motion, and through James Webb's observations, we are now doing so closer to the universe's beginning than ever before. This understanding gently reframes our place within it. We are not observers looking outward from a stable center, but participants embedded in the same expansion we measure. The light arriving at our telescopes has been shaped by the same physical laws that shape our own existence. Scale becomes a shared condition, something we inhabit as much as something we observe. As astronomers refine their measurements, scale grows clearer but never simpler. Each improvement reveals not just farther distances, but finer structure within those distances. The universe shows patterns across vast ranges, from clusters of galaxies down to the subtle filaments that connect them. Scale stretches across these ranges, smoothly, without sharp breaks, suggesting an underlying coherence beneath the immensity. By the time scale is fully considered in observational terms, it no longer feels overwhelming. It feels methodical, almost intimate. The universe does not reveal its size through sudden revelation, but through accumulated evidence. One photon arrives, then another, each adding a small piece to a much larger picture. Over time, those pieces assemble into a sense of depth that is earned rather than assumed. This is the foundation upon which all later discoveries rest. Before new instruments can change what we see, scale must already be understood as something physical, temporal, and constrained by light itself. Only then does it become possible to recognize when that scale shifts, when the universe appears deeper, denser, or more complex than expected. And it is from this quiet, patient understanding of scale that the next layer of discovery naturally begins. Left on its own, human vision is almost completely blind to scale. The eye evolved to navigate nearby space, to recognize faces, judge distance, and track motion under a bright sky. Even on the clearest night, it gathers only a small trickle of light, enough to reveal a few thousand stars and the faint glow of the Milky Way. Beyond that, the universe does not fade gradually. It simply disappears. This is not because there is nothing there, but because our eyes are not built to wait. Light from distant objects arrives sparsely, sometimes one photon at a time, spread across vast areas of space. The human eye cannot accumulate those photons. It must respond quickly, in fractions of a second, or the signal is lost. As a result, most of the universe remains invisible to us, not hidden by distance alone, but by time. Telescopes exist to solve this exact problem. At their core, they do something very simple. They collect light patiently. Instead of glancing, they listen. A telescope gathers photons over minutes, hours, sometimes days, allowing faint signals to slowly rise above the background of darkness. What the eye cannot hold on to, an instrument can preserve. This changes everything about scale. With a telescope, the universe does not suddenly become larger. It becomes measurable. Each improvement in light collection extends the distance from which information can reach us in a meaningful way. The boundary of what we can know shifts outward, not because reality has changed, but because our ability to receive it has improved. This is why the cosmic horizon is not defined by imagination or theory alone. It is defined by instruments. The observable universe is shaped by how much light we can gather, how long we can gather it, and how sensitively we can detect it once it arrives. Without telescopes, the universe would appear shallow and small, not because it is, but because we would have no way to perceive its depth. There is also another limitation quietly at work. Human vision is restricted to a narrow band of light. We see only a small slice of the electromagnetic spectrum, tuned to the light of our sun and the conditions of Earth. But the universe does not confine itself to this range. Over vast distances, light stretches as space expands, slipping out of visible colors into longer wavelengths. By the time it reaches us, much of the oldest light in the universe has become invisible to our eyes entirely. Telescopes extend vision not just by collecting more light, but by changing what kind of light we can see. They translate signals that would otherwise pass through us unnoticed into data we can measure. In doing so, they redefine the cosmic horizon again, allowing the universe to speak in forms our biology never prepared us to hear. What emerges is a humbling realization. The universe we perceive is not the universe as it is, but the universe filtered through our tools. Every boundary we draw around what is observable is also a boundary around our technology. When a telescope improves, the horizon moves. When it stagnates, the horizon holds still. This does not make our knowledge fragile. It makes it honest. Astronomers are careful to distinguish between the universe itself and the portion of it that can be observed with current instruments. The cosmic horizon is not an edge in space. It is a line drawn by patience, sensitivity, and engineering. As telescopes grow more powerful, they do not erase this horizon. They redraw it. Each new instrument pushes it outward slightly, revealing that what once seemed like the farthest reach was only a nearer boundary all along. Scale expands not in leaps, but in careful increments, guided by hardware rather than hope. In this way, telescopes become extensions of time as much as of sight. They allow us to wait longer for light, to notice signals that would otherwise be lost to darkness. They transform the universe from something glimpsed into something studied, from something imagined into something measured. By understanding these limits, the idea of scale becomes grounded again. It is no longer mysterious that the universe appears to grow as our tools improve. It would be strange if it did not. The universe has always been vast. What changes is our capacity to meet it where it is, with instruments quiet enough, patient enough, and sensitive enough to let its most distant light finally arrive. By the time telescopes had firmly defined our cosmic horizon, astronomers began to do something more ambitious than simply looking farther. They started to map, not in the sense of drawing borders, but in the sense of building a coherent picture of how matter is arranged across space and time. Telescopes became tools not just of discovery, but of structure. Early optical telescopes revealed stars as suns scattered through space, and galaxies as distant systems beyond our own. With each increase in mirror size and precision, the universe unfolded outward in layers. Spiral galaxies emerged with clear shapes. Elliptical galaxies revealed smooth, ancient populations of stars. Clusters of galaxies appeared, bound together by gravity, suggesting that matter was not randomly distributed, but organized on enormous scales. As observations improved, patterns began to form. Galaxies were not evenly sprinkled across the cosmos. They gathered into groups, then clusters, then long filaments stretching across vast distances. Between these filaments lay immense voids, regions with very few galaxies at all. The universe, it turned out, had a large-scale structure, something like a cosmic web, woven from gravity and time. Telescopes like Hubble played a central role in revealing this structure. By observing deep fields of sky for extended periods, they showed that what appeared empty at first glance was in fact crowded with galaxies. Hundreds, then thousands, appeared in regions once thought blank. Each deep field expanded the known inventory of the universe and hinted at just how much lay beyond ordinary perception. Yet, even as this picture grew more detailed, its limitations became increasingly clear. Optical telescopes depend on visible light, and visible light is easily obscured. Dust within galaxies absorbs it. Gas clouds scatter it, and over great distances, cosmic expansion stretches it beyond the visible range altogether. The farther astronomers looked, the more the universe seemed to slip out of reach, not because it ended, but because its light changed form. Hubble could see far, but not far enough. It revealed galaxies when the universe was already mature, already structured. The earliest stages of galaxy formation remained faint and elusive. The deeper Hubble looked, the redder and dimmer those galaxies became, until they hovered at the edge of detectability. The maps began to thin out exactly where the most interesting questions arose. Another limit appeared in time. Hubble could observe galaxies billions of years in the past, but there was a growing sense that something was missing. Models of cosmic evolution suggested that galaxies should form gradually, assembling mass over long periods. Yet, even at the limits of Hubble's reach, galaxies already looked surprisingly large and organized. The earliest phases of assembly seemed to be happening beyond the telescope's grasp. This created a quiet tension between observation and theory. Astronomers could trace the universe back to a certain point with confidence, but before that, the map blurred. The cosmic web appeared to vanish, not because it was absent, but because the tools were no longer sensitive to its faintest threads. The universe, it seemed, was still speaking, but in a language older and softer than visible light could capture. Previous telescopes also faced limits of resolution. As objects grew more distant, their light spread thinner across detectors. Galaxies that were distinct nearby became smudges at extreme distances. Details about their shapes, sizes, and internal structure were lost. Mapping the universe at those depths meant accepting a lower level of clarity, trading detail for reach. Despite these limits, something remarkable happened. Even with incomplete maps, astronomers could infer the universe's large-scale behavior. By counting galaxies, measuring their distances, and tracking their motion, they uncovered evidence for cosmic expansion, dark matter, and dark energy. Telescopes did not need to see everything to reveal how the universe behaved overall. Still, there was a sense of standing at a threshold. The maps drawn by previous observatories were impressive, but they felt provisional. They showed where matter was, but not how it first gathered. They revealed structure, but not its earliest scaffolding. The universe's childhood remained mostly hidden, implied rather than observed. This was not a failure of imagination or effort. It was a consequence of physics. Light from the earliest galaxies had traveled for so long that it had been stretched into infrared wavelengths. By the time it reached Earth, it carried information that optical instruments were never designed to receive. The maps stopped, not because the universe ran out, but because the detectors did. Astronomers knew this. They understood that the next leap in understanding would not come from refining the same kind of telescope, but from changing how the universe was observed altogether. Mapping the true scale of the cosmos required a different window, one tuned to the universe's oldest, faintest signals. In this sense, the limits of previous telescopes were not endpoints. They were signposts. Each boundary marked not the edge of knowledge, but the place where a new kind of instrument would be required. The universe had revealed just enough to show that there was more to see. If only we could learn to look differently. By the time James Webb was conceived, astronomers were standing on a map that felt both expansive and incomplete. They could see the architecture of the cosmos, but not its foundations. They could trace structure across billions of light years, but not its first emergence. The scale of the universe was visible, but its earliest depth remained just beyond reach. And it was precisely at that boundary, where previous telescopes fell silent, that the next stage of discovery was waiting. At the boundary where earlier telescopes reached their limits, the problem was no longer one of ambition, but of physics. The universe was still sending its light, but that light had changed. Over billions of years of travel through expanding space, it had been stretched, diluted, and shifted into wavelengths that older instruments could barely register. To see farther meant not just seeing more faintly, but seeing differently. This is where the James Webb Space Telescope enters the story, not as a larger version of what came before, but as a fundamentally different kind of observer. Webb was designed from the beginning to measure the universe in infrared light, the regime where the oldest and most distant signals now reside. This choice alone reshapes what scale means, because it aligns the instrument with the actual condition of the early universe, rather than forcing ancient light to fit into human expectations. Infrared light carries information that visible light cannot, especially at extreme distances. As space expands, it stretches light waves, shifting them toward longer wavelengths. A galaxy that once shone brightly in visible light billions of years ago now sends that same light to us in infrared form. Previous telescopes could sense only the faintest edge of this signal. Webb was built to receive it fully. But sensitivity is only part of the difference. Webb's mirror is not just large, but segmented and precisely shaped, allowing it to collect vast amounts of faint infrared light while maintaining sharp resolution. Each segment works in concert, focusing photons that have traveled for nearly the entire age of the universe into a coherent image. Scale becomes clearer not because objects are magnified, but because their light is finally gathered efficiently. Equally important is where Webb operates. Unlike earlier space telescopes that orbited relatively close to Earth, Webb sits far away, in a region of space where gravitational forces balance in a way that allows for extraordinary stability. There, shielded from the heat of Earth, Moon, and Sun, Webb can remain extremely cold. This matters because infrared observation is a delicate act. Heat itself glows in infrared. Any warmth from the telescope would overwhelm the faint cosmic signals it is meant to detect. Webb's massive sunshield exists for this reason alone. It blocks heat so effectively that the telescope can cool to temperatures where its own emission becomes negligible. In that cold, quiet environment, Webb listens to the universe without drowning it out. Scale, here, is not just about distance, but about silence. The quieter the instrument, the deeper it can hear. This quiet reveals a universe that was previously muted. Early galaxies that once hovered at the threshold of detection now appear with clarity. Their shapes, sizes, and structures emerge not as guesses, but as measured realities. Webb does not merely extend the map drawn by earlier telescopes. It sharpens it, filling in regions that were previously blurred or missing altogether. What makes this difference profound is that it changes the quality of knowledge, not just the quantity. Before Webb, astronomers often inferred the existence of early galaxies indirectly, through statistical hints or partial signals. With Webb, those galaxies become observable entities. Their light is captured, analyzed, and compared in detail. Scale transitions from being extrapolated to being observed. Webb also excels at something subtler. It does not just detect distant objects, it dissects their light. By spreading incoming infrared light into its component, wavelengths, Webb reveals information about composition, temperature, and motion. This allows astronomers to see not just where early galaxies are, but what they are made of and how they behave. Scale becomes richer, layered with physical meaning rather than simple extent. Because of this, distance no longer feels like an empty gap. It becomes a medium filled with evolving matter. Webb shows that early galaxies are not uniform points, but complex systems with internal structure, star formation, and chemical diversity. The universe, even at its greatest depths, is already busy and organized in ways that were once thought impossible to observe. Another fundamental difference lies in Webb's ability to look through cosmic dust. Infrared light passes through dust clouds that block visible light, revealing regions where stars and galaxies are actively forming. This allows Webb to trace the buildup of structure from within, seeing not just the end results, but the processes themselves. Scale now includes formation, not just arrangement. Taken together, these capabilities shift the meaning of observation. Webb is not extending our reach by a small margin. It is aligning observation with cosmic reality. It sees the universe in the wavelengths where its earliest history naturally resides. It operates in conditions that minimize interference. It measures with a patience that matches the age of the signals it receives. This alignment is what makes Webb transformative. It does not force ancient light into modern categories. It meets it on its own terms. And in doing so, it changes how far scale can truly extend. What once appeared as a distant, indistinct edge now resolves into a populated, structured landscape. At this point, scale is no longer constrained primarily by sensitivity or resolution. It becomes constrained by time itself. Webb approaches the limits set by the universe's own history, gathering light from epochs so early that they border the moment when the first stars ignited. The observable universe, which once felt shallow and incomplete, now reveals a depth that matches theoretical expectation and then quietly exceeds it. This is the crucial shift. Webb does not just add detail to the universe we already knew. It reveals that the universe we thought we knew was missing entire layers. Scale expands not because the universe has changed, but because our measurements have finally caught up with its true extent. Once Webb aligns itself with infrared light, distance quietly transforms into something else. It becomes time. Not metaphorically, but physically. The farther light has traveled through the expanding universe, the more its original color has been stretched. What began as energetic starlight billions of years ago arrives at Webb as a longer, gentler wave, carrying with it a precise record of how much the universe has grown since it was emitted. This stretching is not an obstacle. It is a message. Every shift toward infrared encodes the history of expansion along the light's path. When Webb receives that light, it is not merely detecting something distant. It is intercepting a signal that has been in motion since the universe was young. Looking deeper into space becomes an act of looking earlier into cosmic history, because the two are inseparably linked by expansion itself. In the early universe, the first stars and galaxies formed in an environment very different from today. Matter was denser, space was smaller. Light did not need to travel far before encountering other structures. As the universe expanded, those early signals were carried outward, stretched along the way. By the time they reach us now, their original visible light has shifted fully into infrared. Without the ability to see in those wavelengths, the earliest chapters of the universe remain invisible, no matter how large a telescope might be. This is why infrared vision is not an upgrade, but a necessity. Webb does not peer farther simply by seeing fainter objects. It sees objects whose light has been fundamentally transformed by time. In doing so, it accesses eras that were previously inferred but never directly observed. The universe's timeline, once compressed into theory and simulation, begins to unfold through measurement. As Webb looks farther back, galaxies begin to change character. They appear smaller, less orderly, more irregular. This is not because they are poorly resolved, but because they are genuinely young. Their stars are forming rapidly. Their shapes have not yet settled into familiar spirals or smooth ellipses. Webb shows these early systems as they actually were, not as softened impressions at the edge of detectability. What becomes clear is that cosmic history is not evenly paced. The early universe was a period of rapid change. Stars ignited quickly. Galaxies assembled faster than expected. Structure emerged in bursts rather than gradual steps. Infrared observation reveals this acceleration directly because it allows Webb to sample light from closely spaced moments in the universe's youth. Time at these depths feels compressed. This compression reshapes our sense of scale again. The observable universe is not just deep, it is layered unevenly. Billions of years near the present contain relatively subtle changes, while the first few 100 million years hold dramatic transformations. Webb's ability to see into those earliest layers makes scale feel dynamic, as though the universe's depth is weighted toward its beginning. Another consequence of infrared vision is that it clarifies the relationship between distance and expansion. When Webb measures the wavelength shift of distant light, it is measuring how much space has grown during that light's journey. This allows astronomers to reconstruct not just where early galaxies were, but how the universe itself behaved while they formed. Scale becomes inseparable from cosmic growth rates, not just positions. This also tightens the connection between observation and theory. Models of cosmic expansion and galaxy formation make specific predictions about what early galaxies should look like at different times. Webb's infrared data tests those predictions directly. When observations align with theory, confidence deepens. When they diverge, assumptions must be revised. Scale stops being a backdrop and becomes an active constraint on understanding. As Webb approaches the earliest observable epochs, the nature of light grows even more fragile. Signals become extremely faint. Individual photons may represent entire stellar populations compressed into a whisper of energy. Webb's instruments are tuned to recognize these whispers, distinguishing them from background noise with extraordinary precision. At this edge, observation becomes an act of trust between physics and engineering. What Webb reveals is that the early universe was already richly structured. Galaxies existed earlier than expected. Some were surprisingly massive for their age. This does not simply add detail to cosmic history. It stretches the timeline itself, suggesting that the processes of formation and growth were more efficient than previously assumed. The universe, it seems, wasted little time becoming complex. This realization feeds back into the idea of scale in a profound way. If galaxies formed earlier and faster, then the visible depth of the universe contains more structure packed into less time. Scale becomes denser. The observable universe is not just large in extent, but crowded with events, even near its temporal edge. Infrared observation also reveals how interstellar gas and dust behaved in these early epochs. Webb can see the raw material of stars glowing softly in wavelengths that visible telescopes miss entirely. This shows that the universe's earliest light was often filtered through thick clouds, emerging gradually as stars ignited and cleared their surroundings. Time here is marked not just by distance, but by transformation. Through this lens, the universe's history feels less like a straight line and more like a gradual brightening. Early light struggles to emerge, stretched and softened by expansion, until instruments sensitive enough are ready to receive it. Webb arrives at precisely the moment when those ancient signals can finally be gathered in meaningful numbers. What results is a rebalanced picture of cosmic time. The early universe is no longer a dim prelude quickly passed over on the way to familiar galaxies. It becomes a central chapter, rich with structure and activity. Scale, once thought to thin out near the beginning, instead thickens with complexity. At this depth, the observable universe feels almost complete, not because everything is known, but because the boundary of observation now aligns closely with the boundary of cosmic history itself. Webb cannot see beyond the first light, but it can approach it closely enough that the remaining gap feels narrow and well-defined. This is the quiet power of infrared vision. It does not dramatize the past, it simply restores it. By meeting ancient light in the form it naturally arrives, Webb allows the universe to reveal its own timeline with minimal distortion. Distance becomes history, scale becomes memory, and the universe, once stretched thin by time, begins to feel whole again, even at its farthest edge. When the first deep field images from Webb arrived, they did not announce themselves with spectacle. They did something quieter and far more unsettling. They showed that the universe, at extreme depths, was not sparse. It was crowded. Regions of sky once thought nearly empty were suddenly filled with galaxies, layered behind one another, extending far beyond what earlier telescopes had suggested. A deep field is a simple idea executed with patience. The telescope fixes its gaze on a small, seemingly unremarkable patch of sky, and collects light for an extended period. What begins as darkness gradually resolves into structure as photons accumulate. With Webb, this accumulation reached a new threshold. The images revealed not dozens or hundreds of galaxies, but thousands, packed into a region small enough to be covered by a grain of sand held at arm's length. What was immediately striking was not just the number of galaxies, but their apparent maturity. Many of them appeared large, well-defined, and surprisingly organized, even though their light had been traveling since the universe was very young. According to existing models, such structure was expected to take much longer to develop. Yet here it was, already present near the edge of observation. This forced an instant recalibration of scale. If so many galaxies existed so early, then the universe had built complexity faster than assumed. The deep field was not merely extending the map outward. It was compressing cosmic history inward, showing that more happened sooner than expected. Scale became denser, filled with more structure per unit of time. Another immediate revelation was depth within depth. The images did not flatten the universe into a single layer of distant objects. They showed galaxies at many different distances stacked along the same line of sight. Some were relatively nearby in cosmic terms. Others were so distant that their light originated only a few 100 million years after the beginning. The universe revealed itself as a vertical arrangement of time, not a flat panorama. This verticality matters. it means that every deep field image is also a timeline. By examining the colors and brightness of these galaxies, astronomers can estimate their distances and ages. Webb's infrared sensitivity makes these estimates far more reliable because it captures the stretched light directly rather than inferring it indirectly. The result is a depth measurement that feels anchored rather than speculative. The sheer density of galaxies also hinted at something else. If such a small region contained so much structure, then the universe as a whole must be vastly richer than previous surveys suggested. The observable universe did not just grow larger, it grew more populated. Scale expanded not only outward, but inward, filling previously empty conceptual space with real objects. There was also an emotional shift within the scientific community, though it was expressed cautiously. Surprise does not often appear openly in early data releases, but the implications were clear. These images were not just confirming expectations, they were challenging them. The early universe was not a quiet, slowly assembling place. It was already active, busy, and architecturally complex. The deep fields also clarified the role of darkness itself. Much of the image consisted of faint, reddish smudges that would have been invisible to earlier instruments. These were not artifacts or noise. They were galaxies whose light had been stretched almost beyond recognition. Webb showed that the universe's most ancient structures are not hidden by distance alone, but by subtlety. They require sensitivity, not brightness, to reveal. Another important detail emerged in the shapes of these early galaxies. Many were irregular, asymmetric, and compact, suggesting rapid star formation and frequent interactions. Collisions and mergers appeared common. This indicated that the early universe was a turbulent place, where gravity worked quickly and aggressively. Structure did not emerge gently, it assembled through motion and conflict. This turbulence has consequences for scale. It suggests that the large-scale structure seen today arose from a far more chaotic beginning than once thought. The cosmic web, with its smooth filaments and vast voids, likely emerged from an environment rich in motion and variation. Webb's deep fields offer the first direct glimpse of that formative chaos. The images also revealed a continuity that was not guaranteed. Despite their youth, many early galaxies already showed signs of chemical complexity. Elements heavier than hydrogen and helium were present, implying that multiple generations of stars had already lived and died. This pushed the timeline of stellar evolution earlier, tightening the window in which the universe transitioned from simplicity to richness. What makes these revelations powerful is that they come from direct observation. Before Webb, such claims would have rested heavily on models and indirect inference. Now they are grounded in light that has actually arrived. Scale shifts from theoretical expectation to empirical reality, and that shift carries weight. The deep fields also changed how astronomers think about emptiness. Regions once described as blank sky are now understood as crowded vistas waiting for sufficient sensitivity. Darkness becomes provisional. It signals not absence, but unread signals. This reframes future exploration. There is no reason to assume that any region of sky is truly empty, only that it has not yet been listened to deeply enough. As these images were studied further, their implications continued to spread. If early galaxies were more numerous and massive than expected, then models of dark matter distribution, star formation efficiency, and cosmic expansion would need adjustment. Scale is interconnected. change it in one place, and it ripples everywhere. What Webb's first deep fields ultimately revealed was not a single surprise, but a pattern. The universe, when observed at sufficient depth and sensitivity, appears more active, more crowded, and more efficient at building structure than previous data suggested. The early cosmos was not a tentative beginning. It was already underway. In this light, the deep fields feel less like photographs and more like disclosures. They do not simply show what is out there. They show what has always been out there, waiting for the right conditions to be noticed. Scale, once stretched thin by uncertainty, thickens again with evidence. By revealing so much in such a small slice of sky, Webb demonstrated that our previous sense of the universe's depth was conservative. The observable universe is not just wider than we thought. It is busier, richer, and more densely structured at every accessible level. This is why the first deep field images matter so deeply. They did not answer a single question. They changed the tone of inquiry itself. The universe stopped looking reluctant to reveal its early history. It appeared almost eager, provided we were finally equipped to see it. Once the first deep field images were absorbed, their most profound effect began to surface quietly. It was not just that the universe appeared richer or more active. It was that the boundary of what counted as observable had subtly shifted. The apparent size of the universe we can see no longer aligned with earlier expectations, and that misalignment carried deep consequences. The observable universe is often imagined as a sphere whose size is fixed by the age of the universe and the speed of light. In a strict sense, that boundary has not moved. Light has still had the same amount of time to travel. But what Webb revealed is that the effective edge of meaningful observation had been underestimated. There was more structure, more light, and more complexity arriving from near that boundary than models had prepared us for. This matters because scale is not only about maximum distance. It is also about how much information is contained within that distance. If the earliest observable regions contain unexpectedly mature galaxies, then the universe we can study in detail extends closer to its beginning than previously assumed. The usable depth of the observable universe increases, even if the theoretical horizon remains the same. Before Webb, the early universe appeared thin. Few galaxies were visible, and those that were detected seemed marginal and incomplete. This led to an implicit compression of meaningful structure into later cosmic times. The first several hundred million years were treated as a sparse prelude, important but largely inaccessible. Webb reverses that compression. By revealing abundant, structured galaxies at extreme distances, Webb shows that the universe became observationally rich much earlier. This stretches the timeline over which complexity is directly visible. The observable universe no longer feels like a vast space with a narrow window of detail. It becomes a deep archive, filled with legible structure almost all the way back. Another way to understand this shift is through density. When astronomers estimate the number of galaxies per unit volume, they rely on surveys like deep fields. Webb's images suggest that earlier counts were low, not because galaxies were rare, but because they were faint and redshifted beyond detection. Increasing those counts effectively fills in large portions of cosmic volume that were previously underrepresented. As those volumes fill with real objects, the universe's apparent scale expands. Not outward, but inward. Regions that once contributed little to our picture of cosmic structure now become central. The observable universe grows more uniform in informational content, with fewer empty gaps near its temporal edge. This also affects how distance itself is perceived. When distant regions were sparsely populated in data, they felt remote and abstract. Now they feel tangible. Each additional detected galaxy reduces the sense of remoteness, making even extreme distances feel like part of a continuous landscape rather than a fading boundary. There is a subtle psychological effect here, but it is grounded in measurement. When structure persists farther back in time, the universe feels larger because there is more to engage with at every depth. Scale is experienced not just as separation, but as continuity. These observations also force revisions in how quickly light sources appeared after the universe began. If stars and galaxies formed earlier than expected, then luminous matter began contributing to the observable universe sooner. This increases the amount of light available near the horizon, effectively brightening regions that were once thought nearly dark. Brighter early regions mean that the universe's farthest layers are more accessible to observation. Webb does not just detect isolated points, it reveals populations. This population-level visibility stretches the apparent scale because it allows statistical studies to extend farther back. Patterns, distributions, and correlations can be measured at distances where previously only individual detections were possible. Another important factor is resolution. When distant galaxies can be resolved rather than merely detected, they contribute more fully to our understanding of scale. Size, shape, and internal structure all carry information about formation and environment. Webb's ability to resolve early galaxies turns distant space into something readable rather than speculative. As a result, the observable universe becomes functionally larger. More of it can be analyzed in detail. More of it participates in shaping our understanding of cosmic structure. The boundary between known and unknown shifts closer to the true horizon. This shift also impacts models of cosmic expansion. Observations of early galaxies inform estimates of how quickly the universe grew and how matter clustered during that growth. If early structure is more advanced, then the expansion history inferred from these observations must accommodate that fact. Scale becomes recalibrated, not just in space, but in the dynamics of time itself. There is an important restraint here. Webb does not violate the fundamental limits set by physics. It does not see beyond the observable universe. What it does is reveal that those limits were being approached more closely than we realized. The universe had been generous with information near its edge. We simply lacked the tools to receive it. This realization reshapes expectations for future observation. If so much structure exists near the current observational boundary, then the remaining gap between what is visible and what is theoretically reachable is smaller than once thought. The observable universe feels more complete, more continuous, and more internally consistent. Scale, then, stretches not because space itself has grown, but because our picture of what fills that space has expanded. The universe feels larger because it contains more known structure across more of its depth. What was once a vague edge becomes a populated frontier. In this sense, Webb alters the emotional texture of cosmology without compromising its rigor. The universe no longer recedes into darkness at its earliest times. It remains present, active, and structured almost to the limit of observation. Scale becomes something that holds together from near to far, from now to then. This continuity matters deeply. It suggests that the laws shaping galaxies today were already at work early on, operating efficiently and decisively. The universe did not hesitate to become complex. It did so quickly, and it did so everywhere. As a result, the observable universe feels less like a truncated slice of a larger reality and more like a representative sample of it. While much certainly lies beyond what we can see now carries more weight. It spans more history, more structure, and more meaning than previously assumed. This is how Webb stretches the apparent size of the universe. Not by breaking limits, but by filling them. It shows that the space between here and the horizon is richer than expected, and that richness changes how scale is felt, measured, and understood. The universe remains finite in what it offers to observation, but within those bounds, it has revealed itself to be fuller, deeper, and more densely structured than our earlier maps allowed. Scale, once constrained by absence, is now expanded by presence. As the apparent size of the observable universe stretches, a deeper tension comes into focus. It is not just that there is more to see. It is that what is being seen does not always behave as expected. Among the most striking outcomes of Webb's observations is the presence of massive, well-developed galaxies at times when the universe was thought to be too young to build them. For decades, models of cosmic growth followed a careful sequence. After the universe cooled from its earliest hot state, matter slowly gathered under gravity. Small fluctuations grew first, forming modest structures that gradually merged into larger ones. Galaxies in this picture were patient constructions, assembling mass over long periods. The early universe was expected to host mostly small, fragile systems, still finding their shape. Webb complicates this picture. Its infrared observations reveal galaxies that are not only present, very early, but already substantial. Some contain large numbers of stars. Some show organized structure. Some appear to have completed much of their growth astonishingly fast. These are not faint beginnings. They are confident arrivals. This challenges models not because the models were careless, but because they were constrained by previous data. When early galaxies appeared rare and dim, slow growth made sense. Webb's images suggest that early galaxies were neither rare nor especially slow to mature. The universe seems to have been far more efficient at turning raw material into structure than expected. Efficiency becomes the central question. Gravity alone does not explain rapid assembly. Gas must cool quickly. Stars must form in large numbers without blowing their surroundings apart too soon. Feedback processes that regulate growth today may have behaved differently in the early universe. Webb's observations suggest that conditions favored rapid collapse and sustained star formation. This forces a reevaluation of timelines. If massive galaxies exist earlier, then the window for their formation must be compressed. Processes thought to require 1 billion years may have occurred in a few 100 million. Scale in time tightens. The early universe becomes crowded not just with objects, but with events. There is also an implication for dark matter. Galaxies form within invisible halos of dark matter that provide the gravitational framework for growth. If galaxies assembled faster, then those halos must have formed in concentrated mass earlier as well. Webb's observations indirectly probe the behavior of dark matter at early times, suggesting that the cosmic scaffolding may have been sturdier sooner than expected. This does not overthrow existing theory, but it stresses it. Models can be adjusted. Parameters can shift. but the adjustments must now account for a universe that builds quickly under extreme conditions. Webb has not revealed contradictions so much as accelerations. Another layer of challenge comes from stellar populations. The light from these early galaxies indicates that many contain older stars than expected for their cosmic age. This implies multiple generations of star formation occurring in rapid succession. The universe did not hesitate to recycle matter. It forged stars, enriched its gas with heavier elements, and forged more stars again, all within a remarkably short span. This enrichment matters because it affects cooling. Heavier elements allow gas to shed energy more efficiently, promoting faster collapse and star formation. Webb's observations suggest that this feedback loop may have kicked in earlier, creating a self-reinforcing cycle of growth. The early universe may have been primed for speed. As these details accumulate, scale takes on a new character. The early universe is no longer a simple, quiet foundation beneath later complexity. It is itself complex, active, and densely populated with processes. The apparent size of the universe increases not because it stretches farther, but because more happens in its earliest layers than previously assumed. This also affects how astronomers interpret emptiness. If massive galaxies exist early, then the absence of detection in earlier surveys was not a sign of absence, but of limitation. Entire populations were invisible simply because their light fell outside the range of older instruments. Webb reveals that the universe did not wait to become interesting. The challenge extends to simulations. Computer models of cosmic evolution must now reproduce not only the universe we see today, but the universe Webb reveals in its youth. This demands more detailed physics, finer resolution, and careful treatment of early conditions. The universe is asking for more precise questions. There is a restraint here that is important. Webb does not show that all early galaxies were massive or orderly. Many remain small, chaotic, and transient. What Webb changes is the distribution. The tail of massive objects extends earlier than expected. Scale stretches statistically. The universe's early population includes more extremes. These extremes matter because they anchor understanding. A single massive galaxy at early times would be an anomaly. Many of them imply a trend. Webb's observations suggest that rapid growth was not a rare accident, but a recurring outcome under early cosmic conditions. This reshapes how astronomers think about inevitability. The emergence of structure may be less fragile than once believed. Given gravity, expanding space, and cooling matter, complexity may arise quickly and robustly. The universe seems inclined toward organization, even under tight temporal constraints. As a result, scale feels less linear. The universe does not unfold at a constant pace. It surges early, building much of its structure quickly, then spends billions of years refining, rearranging, and evolving what it has built. Webb exposes that early surge directly. This has philosophical weight only because it is physical. It suggests that the universe's capacity to build is front-loaded. Much of what defines cosmic structure today was already seeded early. The universe we inhabit carries the imprint of a rapid, energetic youth. In practical terms, these challenges energize the field. Models are not broken, they are sharpened. Webb's data provides constraints that are more demanding and more informative. Scale becomes a test, not just a measurement. As astronomers respond, the picture of cosmic growth becomes richer. Early galaxies are no longer treated as tentative prototypes, but as serious contributors to the universe's architecture. The scale of the universe now includes not just how far it extends, but how decisively it built itself from the very beginning. This is the quiet revolution Webb brings. It does not contradict the story of cosmic growth. It deepens it, compresses it, and reveals that the universe was never slow to become what it is. As early massive galaxies force models of growth to adapt, a broader consequence begins to emerge. If structure formed quickly and efficiently, then the material that shaped it must have been arranged in a particular way from the start. The universe's scale is not just about how far it extends or how early galaxies appear. It is also about how matter and energy are distributed across that vast depth. On the largest scales, the universe is governed by a delicate balance. Ordinary matter, the atoms that form stars and galaxies, makes up only a small fraction of the total. Most of the mass is carried by dark matter, an invisible substance that does not emit light but exerts gravity. Dark energy, more elusive still, influences how space itself expands. Together, these components determine how structure grows and where it appears. Webb's observations reach into epochs where this balance was still actively shaping the cosmos. By revealing where early galaxies formed and how massive they became, Webb indirectly maps the underlying distribution of dark matter. Galaxies do not form randomly. They trace the invisible scaffolding laid down by dark matter, gathering where gravity is strongest and remaining sparse where it is weak. The presence of many early galaxies suggests that this scaffolding was already well developed. Dark matter halos must have condensed quickly, creating deep gravitational wells capable of pulling in gas and igniting star formation. This implies that matter was not evenly spread in the early universe. Small differences in density were amplified rapidly, carving out a cosmic landscape rich with peaks and valleys. This landscape defines scale in a new way. Instead of imagining the universe as a smooth expanse with isolated objects scattered through it, Webb encourages a view of a textured cosmos. Dense regions grew dense early. Voids emerged alongside them. The large-scale structure we see today appears not as a late arrangement, but as the matured form of patterns established very early. Energy plays an equally important role in this picture. Star formation releases enormous amounts of radiation, which heats surrounding gas and can slow further growth. In the early universe, however, Webb's observations suggest that this feedback did not prevent rapid assembly. Either energy was released differently, or the environment was dense enough to absorb it without halting collapse. This changes assumptions about how energy regulated structure. As galaxies formed quickly, they began to influence their surroundings. Their radiation ionized nearby gas, altering how matter moved and cooled. Webb allows astronomers to see this interplay directly by observing the glow of gas in early regions. Matter and energy are not separate actors. They continuously shape one another, especially during the universe's formative stages. Another implication concerns how matter clusters over distance. If early galaxies are more numerous and massive, then matter must have been clustered more tightly on small scales while still remaining coherent on large scales. This dual behavior is a hallmark of dark matter-driven growth. Webb's data strengthens the case that dark matter behaved as expected in broad strokes, even if details of galaxy formation need revision. At the same time, the observations refine where dark matter's influence becomes dominant. By comparing the visible mass of early galaxies to their inferred total mass, astronomers can estimate how much unseen matter must be present. Webb's reach into early time improves these estimates, anchoring them in direct observation rather than extrapolation. Dark energy enters the story more subtly. In the early universe, its influence was weaker than it is today. Matter dominated the dynamics, allowing gravity to assemble structure efficiently. Webb's view of rapid early growth fits naturally into this picture. It shows the universe during an era when matter had the upper hand, before accelerated expansion began to pull structures apart. This temporal context matters for scale. The universe's structure did not form under constant conditions. The balance between matter and dark energy shifted over time. Webb captures the universe near the peak of matter's influence, when growth was fastest and most decisive. Scale, then, reflects not just distance and time, but the changing dominance of cosmic ingredients. There is also a compositional insight. Webb's spectral observations reveal the presence of heavier elements in early galaxies. These elements are forged in stars and dispersed by explosions. Their early appearance indicates that matter cycled through stars rapidly. Energy released by these stars reshaped surrounding matter, seeding future generations of structure. This cycling adds texture to scale. Matter is not static as it fills space. It moves, transforms, and reappears in new forms. Webb shows that this process began earlier and progressed faster than once believed. The universe's material content became complex quickly, enriching regions that would later host planets and life. As these details accumulate, the distribution of matter and energy appears less uniform and more intentional in outcome, though not in design. Physical laws operating under early conditions produced a universe that organized itself efficiently. Webb reveals the results of that organization across immense distances. This understanding affects how astronomers interpret emptiness again. Voids are not failures of formation. They are outcomes of matter flowing toward denser regions. Webb's deep reach allows these voids to be seen in contrast to dense filaments even at early times. Scale includes absence as much as presence, shaped by the same forces. The implications ripple forward. If matter clustered early, then later cosmic history is built upon a foundation that was already robust. Galaxy mergers, cluster, formation, and the evolution of large-scale structure all proceed from this early arrangement. Webb's observations push the origin of that arrangement closer to the beginning. What emerges is a universe whose scale is supported by an underlying coherence. Matter and energy did not drift into complexity slowly and hesitantly. They organized under gravity and expansion in a way that produced structure quickly and persistently. Webb's view confirms that coherence by revealing it where it was once invisible. This does not simplify cosmology. It enriches it. The distribution of matter and energy becomes a story that unfolds across time, with different actors dominating at different stages. Webb captures a crucial chapter in that story, when matter's influence was strongest and structure took shape decisively. As a result, the scale of the universe feels more integrated. Distance, time, matter, and energy are no longer separate concepts stitched together by theory. They appear as intertwined aspects of a single evolving system. Webb's observations bring that system into focus at depths that were previously inaccessible. By showing how matter gathered and how energy flowed in the early universe, Webb anchors scale in physical reality. The universe's vastness is not empty space punctuated by rare events. It is a continuous fabric shaped by forces acting everywhere, from the smallest fluctuations to the largest structures. In this view, scale becomes something dynamic and relational. It reflects how matter and energy distribute themselves across expanding space, guided by laws that operate consistently from the beginning. Webb does not reveal a universe that is fundamentally unfamiliar. It reveals one that is more fully itself than we had been able to see. And it is from this fuller picture of distribution, of matter drawn together and energy released, that the final shift in perspective naturally arises. When the universe's scale is understood not just as size, but as structure and process, our sense of position within it begins to change in a subtle but lasting way. When scale is understood as structure, history, and process rather than sheer size, its effect turns inward as well as outward. The universe no longer feels like an incomprehensible expanse with a distant edge. It becomes a continuous environment, one in which every region we can observe participates in the same physical story, governed by the same laws and shaped by the same forces. Webb's revelations subtly alter our sense of proportion. The universe is still vast beyond ordinary intuition, but it is no longer defined by emptiness between rare objects. Instead, it appears densely occupied, active at nearly every depth, and coherent across immense distances. What once felt like a scattered cosmos now feels like a connected whole, where structure persists from the nearby universe all the way back to its earliest visible moments. This coherence matters because it anchors scale emotionally as well as scientifically. When early galaxies are seen forming rapidly and abundantly, the universe stops feeling fragile or tentative. It appears capable, even decisive. Complexity is not a late luxury. It is a natural outcome of physical law acting under the right conditions. The universe does not hesitate to build. Within this context, our own position becomes clearer without becoming smaller in a dismissive sense. Earth does not sit at the center of anything spatially, but it sits within a universe that has been structured and enriched for billions of years. The atoms that make up planets, bodies, and thoughts are products of processes Webb now observes closer to their beginning. Scale connects origin to presence. Webb collapses a psychological distance that once existed between us and the early universe. Those epochs are no longer abstract or unreachable. They are visible, measured, and textured. The light from that time arrives not as a vague glow, but as resolved structure. This makes the universe's history feel less like a remote prologue and more like an extension of the same unfolding reality we inhabit. There is also a shift in humility, but it is a grounded one. Webb does not suggest that humans are insignificant because the universe is large. It suggests that we are participants in a universe that has been understandable from its earliest stages onward. Our tools have matured enough to listen to ancient signals, and those signals respond with clarity rather than silence. In this light, knowledge itself feels differently scaled. Discovery is no longer about piercing an unknowable darkness. It is about refining attention, improving sensitivity, and aligning instruments with reality as it is. Webb demonstrates that the universe has been offering information all along. What changes is our ability to receive it. This reframing also tempers expectations. There will always be limits. There will always be horizons defined by time and physics. Webb does not remove those boundaries. It makes them honest. It shows that within the bounds set by the universe's age, there is far more structure, history, and coherence than we once assumed. The universe revealed by Webb feels mature even at its youngest visible stages. That maturity reflects a cosmos that organizes itself efficiently, governed by laws that operate consistently across time. Scale, in this sense, becomes reassuring. It suggests stability beneath complexity, order beneath apparent chaos. As this understanding settles, the universe no longer feels like something happening far away. It feels like something that has always included us, even before we existed. The same expansion that stretched ancient light now stretches the space around us. The same gravity that assembled early galaxies shaped the stars that seeded our world. Webb does not place humanity at the center of the universe. It does something quieter and more meaningful. It places humanity within a universe that is legible, continuous, and deeply connected across time. Our position is not privileged by location, but by participation in understanding. This is perhaps the most lasting change Webb brings. Scale stops being overwhelming and starts being relational. The universe is vast, but it is not indifferent. It follows rules we can trace, patterns we can recognize, and histories we can reconstruct. Our ability to see far back into time becomes a way of belonging to that history rather than standing apart from it. When we look at Webb's images, we are not witnessing alien realms detached from our experience. We are seeing earlier expressions of the same universe that produced stars, planets, and eventually observers. Scale binds those expressions together rather than separating them. In the end, the true shift is not that the universe is larger than we thought. It is that it is fuller, earlier, and more structurally complete than expected. Webb shows that the universe did not wait to become interesting, and it did not require our presence to be rich with structure. By revealing this, Webb leaves us with a calm recognition. We live inside a universe that has been unfolding with remarkable coherence for nearly its entire history. Our moment within it is brief, but it is connected. The scale that once felt distant now feels continuous, extending smoothly from the first light to the present. And within that continuity, the universe no longer feels like something merely observed. It feels like something we are already a part of, carried forward by the same expansion, shaped by the same forces, and illuminated by light that has been traveling toward understanding since the beginning. As this sense of continuity settles, something subtle changes in how the universe is perceived moment to moment. The sky no longer feels like a backdrop with a few remarkable features scattered across it. It feels layered, almost saturated with history, as though every direction contains not just space, but accumulated time waiting to be noticed. Webb's perspective encourages a quieter kind of attention. When scale is understood as depth rather than distance, looking outward no longer feels like reaching away from ourselves. It feels like tracing a line backward through the same physical story that led here. The expansion that stretches ancient light is still ongoing, still shaping the distances between galaxies, still defining the conditions under which matter gathers and disperses. This ongoing expansion ties the earliest universe to the present in a continuous motion. The same process that carried the first starlight into infrared wavelengths is carrying today's light outward as well. Scale becomes something active, something unfolding, rather than a static measure frozen in space. The universe is not finished expanding, and understanding it is not finished either. What Webb makes clear is that the universe has always been generous with information. It has been sending signals uninterrupted since the first stars ignited. The challenge was never that the universe was silent. It was that the signals were faint, stretched, and required patience to receive. With the right alignment of technology and understanding, those signals resolve into clarity. This clarity has an unexpected calming effect. When structure appears everywhere, even near the limits of observation, uncertainty feels bounded rather than infinite. There is still much we do not know, but what we can know now spans a remarkable portion of cosmic history. Scale feels navigable, not because it is small, but because it is coherent. Webb also reframes anticipation. Future discoveries no longer feel like leaps into the unknown, but like careful extensions of an already visible pattern. If structure exists nearly to the observable edge, then refining sensitivity and resolution promises depth rather than surprise. The universe appears consistent with itself across time. This consistency does not remove wonder, it reshapes it. Wonder emerges not from unpredictability, but from the quiet reliability of physical law operating across unimaginable spans. Gravity gathers matter. Expansion stretches light. Energy flows, matter cools, stars ignite. These processes repeat, scale after scale, epoch after epoch. Within this repetition, variation arises naturally. No two galaxies are identical. No region of space follows exactly the same path. Scale accommodates both order and diversity, and Webb shows that this balance existed from the very beginning. The early universe was not a uniform blur. It was already expressive. As the mind adjusts to this view, the universe feels less like a place to conquer intellectually and more like a system to become fluent in. Webb does not overwhelm with novelty. It invites familiarity. The farther we look, the more recognizable the rules become, even as the settings change. This fluency has consequences for patience. When the universe is understood as layered and continuous, there is less urgency to force conclusions. Observations can accumulate. Patterns can emerge gradually. Scale rewards steadiness rather than speed. In this way, Webb subtly reshapes not only cosmology, but the posture of inquiry itself. Understanding grows by listening longer, by matching the tempo of investigation to the tempo of the universe. Light takes billions of years to arrive. Knowledge does not need to hurry. The universe revealed by Webb feels neither rushed nor withheld. It feels present, available, and structured, extending calmly from the first galaxies to the space around us now. Scale becomes something that can be sat with, traced slowly without strain. And as attention rests there, the universe continues doing what it has always done. Space expands, light travels, matter gathers. Signals move steadily outward, carrying with them the record of everything that has happened so far. Webb simply shows that this record is richer, earlier, and more complete than we once thought, and that it has been arriving all along, patiently, waiting to be received. What Webb ultimately encourages is a different relationship with vastness. Instead of confronting immensity all at once, the universe reveals itself through continuity. Every distant galaxy is connected to nearby space through the same expansion. Every ancient photon follows the same physical rules as light emitted today. Scale becomes something that unfolds step by step, never requiring a leap beyond comprehension. This unfolding reshapes how absence is interpreted. Darkness in the sky no longer implies emptiness or unknowability. It suggests depth that has not yet been fully resolved, signals that remain faint rather than missing. The universe feels less like a puzzle with missing pieces and more like a manuscript whose earlier pages are written in a subtler ink. There is also a quiet shift in trust. Webb demonstrates that the universe behaves consistently across extraordinary spans of time and space. The same laws that govern motion here also governed the first galaxies. This consistency allows understanding to extend confidently outward, knowing that explanation does not dissolve at distance. As a result, the boundary between observation and inference becomes thinner. When enough of the early universe is visible, the remaining unknowns feel constrained rather than limitless. Questions become sharper, more precise, because they are framed within a landscape that is already partially mapped. The universe, seen this way, feels less distant from daily experience. Not smaller, but more familiar in its behavior. Expansion, accumulation, transformation, and change are not exotic ideas confined to cosmology. They are expressions of patterns that operate everywhere, scaled up to a grander stage. Webb also subtly adjusts the pace of curiosity. When the universe is understood as layered rather than abrupt, there is no pressure to rush toward conclusions. Insight accumulates naturally as observation deepens. Scale rewards patience, mirroring the patience with which light itself travels. This patience carries a quiet reassurance. The universe is not withholding its story. It is telling it continuously, in signals that arrive steadily, one after another. Webb simply shows how much of that story has already arrived, waiting for careful attention. As this realization settles, the universe feels less like a frontier and more like a continuum. There is no sharp edge where understanding suddenly fails. There are only gradual transitions, where signals thin, wavelengths stretch further, and observation approaches the limits set by time itself. Within those limits, the universe appears generous. It offers structure almost to the very beginning of observable history. It reveals complexity early and persistently. Scale becomes something rich rather than sparse, filled rather than hollow. And so the universe no longer feels like something distant that we peer into from a small island of certainty. It feels like an extended environment, one that has been evolving continuously, carrying its history forward through light and motion until it intersects with instruments capable of noticing it. Webb's contribution is not to make the universe louder or more dramatic. It makes it clearer. It allows scale to be perceived as a smooth progression rather than an overwhelming jump. The universe reveals itself at a pace that understanding can follow. In that clarity, vastness loses its sharpness. It becomes something that can be traced, revisited, and dwelled within. The sky turns into a record rather than a mystery, and distance becomes a measure of how much history light has carried before arriving. The universe continues expanding. Light continues traveling. Structure continues forming and evolving. None of this pauses for observation. But with each improvement in sensitivity and alignment, more of that ongoing process becomes visible, knitting the immense scale of the cosmos into a coherent, continuous whole. And within that whole, the universe no longer feels distant in spirit, even as it remains vast in extent. It feels present, unfolding steadily, offering its depth one patient signal at a time. What Webb makes quietly apparent is that the universe is not built in disconnected layers. The earliest galaxies are not separated from us by an unbridgeable gap. They are connected by a continuous chain of cause and effect, carried forward by expansion and time. Every moment leads naturally to the next, and scale becomes the expression of that continuity rather than its obstacle. This continuity softens the idea of cosmic remoteness. The early universe does not feel unreachable. It feels earlier, not elsewhere. Its light arrives altered but intact, carrying with it the conditions under which it formed. Webb receives that light without forcing it into familiar forms, allowing it to speak in its own stretched, ancient voice. As a result, the universe begins to feel more patient than immense. It unfolds at a pace set by physical law, not by urgency. Expansion proceeds steadily. Structure emerges where conditions allow. Nothing is rushed, and nothing is arbitrary. Scale reflects this steadiness, stretching smoothly rather than leaping unpredictably. This steadiness offers a kind of orientation. When the universe behaves consistently across time and distance, understanding can grow without anxiety. There is room to observe, to revise, to refine. Knowledge becomes something that accumulates naturally, much like the light Webb gathers, one signal at a time. In this light, the act of observation feels less like intrusion and more like participation. Instruments do not pry secrets from the universe. They align with it. They wait. They listen. And when they are quiet enough, the universe responds with clarity rather than resistance. Webb exemplifies this alignment. It does not impose a narrative on the cosmos. It allows the cosmos to reveal its own structure, depth, and rhythm. Scale emerges not as a dramatic revelation, but as a steady realization that the universe has always been full, even where we once perceived emptiness. As perception adjusts, the universe feels less like an external spectacle and more like an environment extended across time. The same physical laws shaping distant galaxies shape nearby stars, planets, and the conditions that allow observers to exist at all. Scale binds these experiences together rather than separating them. There is a quiet reassurance in this binding. It suggests that understanding does not diminish meaning as distance increases. Instead, meaning becomes distributed. Every region of space participates in the same unfolding process, each at its own stage, each carrying its own history forward through light and motion. The universe revealed by Webb does not ask it to be conquered intellectually. It invites familiarity. The more deeply it is observed, the more its behavior repeats in recognizable ways. Gravity gathers, expansion stretches, energy flows, matter transforms. These processes scale upward smoothly, retaining their character even as their scope grows immense. In this familiarity, vastness loses its sharp edge. It becomes something that can be approached gradually, without strain. The universe does not confront the observer with an ungraspable whole. It reveals itself through sequences, patterns, and layers that understanding can follow naturally. As attention lingers here, scale no longer feels like a challenge to perspective. It feels like a context. The universe is large, but it is not disorienting. It is structured, coherent, and continuous, offering its depth without demanding that it be held all at once. And so the universe remains in motion, expanding quietly, sending its light outward in every direction. Webb continues to receive that light, translating ancient signals into forms we can recognize. With each observation, the universe becomes not smaller, but more legible. Scale, in the end, does not overwhelm. It situates. It places each moment, each structure, each observer within a larger ongoing story that unfolds according to rules both simple and profound. The universe does not hurry this story. It allows it to arrive when it arrives, carried by light that has been traveling since the first stars formed. And with the right kind of attention, that story continues to reveal itself, calmly, patiently, one signal after another. As this sense of legibility deepens, the universe begins to feel less like something revealed in moments of discovery, and more like something continuously present. Scale no longer arrives in shocks or revelations. It settles gradually, the way understanding settles when pieces fit together without force. What Webb quietly demonstrates is that the universe does not guard its early history behind chaos or obscurity. It preserves it, faithfully, encoded in light that moves according to simple rules. Expansion stretches wavelengths. Gravity shapes matter. Time carries signals forward. Nothing is hidden by intention. It is only carried far enough to require patience. That patience becomes part of perception. When scale is approached this way, curiosity slows naturally. There is no need to rush ahead because the universe is not running away. It is expanding, but it is also continuously communicating, sending information outward in all directions at a steady pace. This steadiness reshapes expectation. The unknown no longer feels like an abyss beyond the edge of knowledge. It feels like a continuation, a region where signals are fainter, older, and require finer listening. Scale becomes a gradient rather than a boundary. In this gradient, understanding grows through alignment rather than conquest. Instruments are designed to match the universe's behavior, not overpower it. Webb's success comes from respecting how ancient light arrives, not forcing it into forms it no longer inhabits. As a result, the universe appears remarkably cooperative. Given the right conditions, it reveals structure almost everywhere it can be observed. It does not dissolve into randomness at great distances. It remains patterned, governed, and responsive to measurement. This has a quiet emotional consequence. Vastness no longer produces a sense of insignificance. Instead, it produces continuity. The same physical story that unfolds across billions of light years also unfolds locally, shaping stars, planets, and conditions where observers can exist at all. Scale becomes the medium of connection rather than separation. Distance does not isolate regions of the universe from one another. It links them through shared history, carried by light that preserves information across time. When seen this way, the universe feels less like a place we look into, and more like a process we are embedded within. The expansion that stretches ancient light also stretches the space between nearby galaxies. The gravity that assembled early structures still governs motion today. The rules have not changed. Only the stage has grown. Webb's contribution is to show how much of that stage is already visible, how much of the universe's depth has been quietly accessible all along. Scale reveals itself not as an overwhelming expanse, but as an orderly unfolding that rewards careful attention. As attention rests here, the universe feels calm rather than dramatic. Its history is vast, but it is coherent. Its size is immense, but it is structured. Its beginnings are distant, but they are not erased. Light continues to travel. Space continues to expand. Matter continues to gather and transform. None of this pauses, and none of it needs interpretation to proceed. Understanding simply follows, step by step, as instruments and insight align. In that alignment, the universe becomes something that can be lived with intellectually rather than merely admired from afar. Scale becomes familiar, not because it shrinks, but because it makes sense. and so the universe remains open, extending its depth patiently, carrying its history forward in signals that arrive steadily, ready to be noticed whenever listening becomes quiet enough again. As this quiet familiarity continues to take hold, the universe begins to feel less like a vast unknown and more like a system that has always been willing to be understood. Scale no longer presses outward as something to be confronted. It settles inward as something that can be traced, followed, and lived with intellectually. The distance between here and the earliest galaxies stops feeling like a gap. It becomes a sequence. One moment leads to the next. One structure grows out of another. Light moves forward carrying those moments intact, stretched but not erased. Scale becomes the record of that movement rather than an obstacle to comprehension. In this view, the universe is not divided into epochs that feel disconnected from one another. Its earliest visible light and its present state belong to the same unfolding process. The conditions that allowed the first stars to ignite also shaped the environment that later produced galaxies, planets, and eventually observers capable of noticing the pattern. Webb's contribution lies in revealing how little interruption there is in that pattern. The universe does not suddenly become alien as we look farther back. It becomes younger, denser, and more energetic, but it remains governed by familiar relationships. Gravity still gathers matter. Expansion still stretches space. Energy still flows and transforms. Scale preserves character even as it increases magnitude. This preservation has a grounding effect. It suggests that understanding does not break down at the edges of observation. It thins gradually, the way light thins, becoming fainter but not chaotic. The unknown remains adjacent to the known, not separated by an abrupt boundary. As that adjacency becomes clear, curiosity relaxes. There is room to explore without urgency. The universe is not withholding its meaning. It is revealing it at a pace set by physics rather than expectation. Scale teaches patience by example. There is also a subtle sense of symmetry that emerges. The universe expanded outward from a dense beginning, and understanding expands outward from careful observation. Both proceed incrementally. Both depend on accumulation rather than leaps. Both reward alignment over force. In this symmetry, observation feels less like a spotlight and more like a listening posture. Webb listens deeply into space and time, and the universe responds with structure, not silence. That response suggests that the cosmos has always been intelligible, even when it was inaccessible. As attention stays here, scale becomes something that supports rather than overwhelms thought. It provides context without demanding total grasp. 1 does not need to hold the entire universe at once. It is enough to recognize that each visible layer fits coherently with the next. The universe remains vast, but it no longer feels distant in spirit. Its earliest light participates in the same narrative as the space around us now. The same expansion connects them. The same laws govern them. Scale unifies rather than fragments. And so the universe continues, expanding steadily, carrying its history forward in light that moves patiently through space. Instruments like Webb simply allow more of that history to arrive intact, revealing a cosmos that has been structured, active, and expressive almost from the beginning. In this continuity, scale becomes something that can be returned to, revisited, and deepened without strain. The universe offers its depth gradually, one signal at a time, and understanding follows at the same measured pace, never rushed, never forced, always unfolding alongside the light itself. As the universe continues to reveal itself with this kind of steadiness, another dimension of scale quietly comes into view. Not the scale of distance or time, but the scale of certainty. Webb does not eliminate uncertainty, but it reshapes where uncertainty lives. Instead of surrounding everything beyond a narrow observational window, uncertainty is pushed to more precise edges, confined to questions that are sharper and better defined. This changes the character of not knowing. Before, the early universe felt broadly inaccessible, a region where speculation outpaced observation. Now, much of that region is illuminated well enough that questions can be asked with specificity. How fast did the first stars form? How efficiently did gas cool? How early did heavy elements spread? Scale becomes something that supports inquiry rather than frustrates it. Webb also introduces a new temporal texture to understanding. The universe is no longer divided simply into early and late. It reveals transitional phases with clarity, periods when galaxies were assembling but not yet settled, moments when star formation surged and then regulated itself. Scale acquires granularity, allowing time itself to be examined in finer slices. This granularity matters because it shows that cosmic evolution is not smooth. It proceeds in bursts, pauses, and feedback cycles. Webb's sensitivity makes these patterns visible, especially in the early universe where change happened quickly. Scale, in this sense, contains rhythm. The universe pulses with activity, then settles, then reorganizes, all within the same expanding framework. Another novel shift comes from comparison. Webb allows distant epochs to be studied with a level of detail once reserved for nearby galaxies. This creates a direct dialogue between past and present. Early galaxies can be compared to mature ones, not as abstract ancestors, but as observable systems at different stages of development. Scale collapses distance conceptually by making those comparisons concrete. This comparative power also exposes continuity in complexity. Features once thought to require long cosmic timescales appear much earlier. Disks, bulges, chemical gradients, and star-forming regions emerge sooner than expected. The universe did not slowly invent complexity. It expressed it rapidly, refining rather than originating structure over time. Webb further reframes scale by revealing how localized processes contribute to global structure. Star formation within individual galaxies influences large-scale patterns by shaping how matter and energy move through space. Radiation escapes, gas flows respond, neighboring regions are affected. Small-scale physics scales upward naturally, weaving local events into the universe's overall architecture. This upward scaling reinforces a sense of coherence. The universe does not operate with separate rules at different sizes. The same principles repeat, accumulating effects across distance and time. Webb shows this repetition clearly by connecting detailed observations of early galaxies to the large-scale structure that emerges later. There is also a shift in how future horizons are imagined. Webb suggests that the next limits we encounter will not be walls, but gradients of diminishing signal. The universe does not end abruptly at what we can observe. It fades into quieter regimes where light becomes scarcer and harder to distinguish. Scale invites refinement rather than confrontation. This invites a different kind of ambition. Progress no longer depends solely on building larger instruments. It depends on learning how to extract meaning from faint signals, how to listen more carefully, how to integrate information across wavelengths and time. Scale becomes an exercise in sensitivity, not conquest. As this perspective settles, the universe feels increasingly conversational. It sends signals continuously. Instruments respond. Understanding grows through exchange rather than extraction. Webb exemplifies this relationship, acting less like a probe and more like a translator between epochs. In this exchange, scale becomes something lived with intellectually. It does not need to be resolved fully to be meaningful. Its value lies in how it situates every observation within a broader, connected context. Each new detail adds depth rather than confusion. The universe continues expanding. New light continues its long journey. Some of it will not arrive for billions of years. Some of it will arrive altered beyond easy recognition. Yet Webb shows that even near the limits of what can be seen, the universe remains structured, expressive, and responsive to careful attention. This suggests that scale is not an adversary to understanding. It is the medium through which understanding unfolds. The universe is large not to overwhelm, but to allow patterns to emerge gradually, layered across time. And so the universe remains open, not as a challenge to be solved, but as a process to be noticed. Scale does not demand mastery. It invites familiarity. With each observation, the cosmos offers another quiet confirmation that it has been telling the same coherent story from the beginning, carried patiently forward by light, waiting for moments when listening becomes deep enough to hear it. As attention stays with this unfolding picture, scale begins to express itself in yet another way, through the quiet resilience of the universe's patterns. Even as conditions change dramatically across time, those patterns persist. Matter gathers, light travels, space expands. The details vary, but the structure of behavior remains recognizable. This persistence gives scale a kind of stability, even across billions of years. Webb's observations suggest that the universe is not improvising its way forward. It is following a set of deeply rooted tendencies that assert themselves wherever conditions allow. When matter cools, gravity gathers it. When stars ignite, they reshape their surroundings. When space expands, light stretches but continues onward. Scale magnifies these tendencies without distorting them. This magnification reveals something subtle about cosmic change. The universe evolves, but it does not reinvent itself. Early galaxies differ from modern ones, but not in kind. They are faster, denser, more chaotic, yet they follow the same principles. Scale becomes a lens that shows how the same rules express themselves under different pressures. As this becomes clear, the universe begins to feel less contingent. Its history does not appear fragile, dependent on narrow coincidences. Instead, it appears robust. Given expansion, gravity, and matter, structure seems almost unavoidable. Webb's glimpse of early abundance reinforces this sense. Complexity emerges not reluctantly, but readily. This readiness reframes how beginnings are understood. The early universe is often imagined as a delicate phase, where small changes could have led to vastly different outcomes. Webb suggests something slightly different. While details matter, the broad emergence of structure appears strongly favored. Scale amplifies this favoring, showing that once conditions are set, the universe commits. This commitment has consequences for how we think about rarity. Galaxies, stars, and chemical complexity may not be exceptional outcomes. They may be common expressions of cosmic evolution. Webb's crowded deep fields hint at this abundance, implying that what we see locally may be typical rather than unusual. That implication extends outward gently, without assertion. It does not claim certainty about what lies beyond the observable universe. It simply notes that within what can be seen, structure arises repeatedly and early. Scale supports repetition as much as uniqueness. As repetition becomes visible, comparison deepens understanding. Patterns can be traced across epochs, revealing how similar processes unfold under different initial conditions. Webb enables these comparisons by placing early and late structures on the same observational footing. Scale becomes comparative rather than isolating. This comparison also tempers the drama often associated with cosmic distances. When early galaxies look like understandable precursors rather than alien anomalies, the universe feels less divided by time. The past remains present through continuity of behavior. There is also a practical shift in how exploration is imagined. Instead of seeking singular breakthroughs, progress becomes cumulative. Each observation refines context. Each faint detection fills in another layer. Scale rewards accumulation rather than spectacle. This accumulation mirrors the universe's own method. Structure builds from small fluctuations. Galaxies assemble from repeated events. Complexity arises through layering rather than leaps. Webb's way of seeing aligns with this method, gathering light patiently and letting patterns emerge gradually. As this alignment becomes familiar, the universe feels less like an object of study and more like a system with which observation is synchronized. Instruments wait. Light arrives. Understanding follows. Scale becomes the shared tempo between cosmos and comprehension. The sky, viewed through this lens, no longer feels static. It feels active even when nothing seems to change. Signals are always in transit. Processes are always unfolding beyond immediate perception. Scale includes motion that is too slow or too vast to notice directly, yet always present. This awareness reshapes stillness. Even the quietest regions of space are participating in expansion, in gravitational balance, in the slow redistribution of matter and energy. Scale ensures that nothing is truly isolated from the universe's overall evolution. As this sense settles, curiosity becomes less about reaching an endpoint and more about staying attentive. There is no final image that completes understanding. There is only increasing resolution, increasing context, increasing depth. Webb demonstrates that depth is not exhausting. It is stabilizing. The more of the universe's history becomes visible, the more coherent the whole appears. Scale does not fracture meaning. It distributes it. And so the universe continues, expansive yet orderly, ancient yet ongoing. Light keeps traveling. Space keeps stretching. Structure keeps emerging and transforming. None of this waits to be observed, yet all of it remains observable in principle, given enough patience and care. Scale, in this light, is not a challenge to presence. It is the condition that makes presence possible, allowing the universe to unfold slowly enough for understanding to arise alongside it, one quiet signal at a time. As this steady awareness continues, scale begins to show itself not only in what is seen, but in how seeing itself changes over time. Each generation of observation does not replace the last. It settles on top of it, adding thickness to understanding rather than overturning it. The universe becomes something known by accumulation, much like the way light itself accumulates on a detector, slowly separating signal from darkness. Webb reveals that scale has memory, Earlier observations still matter. They provide context, contrast, and constraint. What changes is resolution. What was once a blur becomes textured. What was once inferred becomes visible. Scale does not leap forward, it clarifies. This clarification reshapes how beginnings are imagined. The first stars and galaxies no longer sit at the edge of a conceptual abyss. They occupy a region that is now continuous with everything that followed. The universe's origin does not feel like a singular explosion receding into obscurity. It feels like the first moment of a long, uninterrupted process that remains visible almost to its start. In this view, time itself gains structure. Early epochs are no longer compressed into a single distant haze. They separate into phases with distinct character, periods of rapid star formation, phases of chemical enrichment, intervals where galaxies collide, settle, and reorganize. Scale allows time to be experienced with depth rather than distance. This depth changes how causality is felt. When early structure is visible in detail, the link between cause and effect strengthens. The conditions present in the early universe can be traced forward, shaping later outcomes. Scale becomes the medium through which consequences travel, preserved in light and structure. Webb's observations reinforce the idea that the universe is legible because it is lawful. Nothing observed at great distance violates the rules known locally. Instead, those rules reveal their full range when given enough space and time to operate. Scale becomes the arena in which simplicity generates richness. This richness is not chaotic, it is patterned. Even in the most distant images, structure repeats in recognizable forms: clusters, filaments, concentrations, voids. The same motifs appear again and again, adjusted by circumstance but never abandoned. Scale magnifies pattern without erasing it. As pattern becomes evident across distance and time, the universe feels less fragmented. There is no sharp divide between early and late, small and large, simple and complex. These are gradients, not categories. Scale smooths transitions rather than enforcing boundaries. This smoothing has an emotional resonance. It allows vastness to be held without tension. The universe does not demand to be grasped in total. It offers itself in layers that can be approached gradually, revisited, and integrated. Webb's role in this process is quiet but decisive. It does not claim to show everything. It shows enough to demonstrate continuity, enough to show that the universe remains structured, even where it was once thought to thin into abstraction. As understanding rests here, curiosity becomes less restless. It does not need to jump ahead to the next unknown. It can remain present with what is already visible, trusting that deeper layers will reveal themselves in time. The universe continues to expand, and light continues its journey outward. Some signals will arrive far in the future, carrying information from regions that are only now becoming luminous. Scale guarantees that the story is unfinished, but not inaccessible. In this unfinished state, the universe feels alive in a measured way, not dramatic, not urgent, but persistent. Its processes repeat, refine, and extend. Webb allows a glimpse of this persistence across nearly the entire observable timeline. And so scale becomes something lived alongside, not something confronted. It shapes perception quietly, aligning understanding with the tempo of the cosmos itself. The universe does not rush to reveal its depth. It reveals it steadily, carried by light that moves patiently through expanding space. In that patience, there is room for attention, for revision, for wonder, That does not depend on surprise. The universe remains vast, but it is no longer distant in meaning. It unfolds coherently, offering its history in signals that continue to arrive, calmly, endlessly, one after another. As this sense of accumulated depth continues to unfold, scale begins to express itself through endurance. Not endurance as permanence, but as continuity across change. Galaxies form, merge, and transform. Stars ignite and fade. Yet the underlying processes persist, carrying structure forward even as individual components evolve. Scale becomes the measure of how long patterns can survive motion. Webb's view suggests that the universe is not fragile across time. Its structures are not easily erased by expansion or transformation. Instead, they adapt. Filaments stretch but remain connected. Clusters rearrange but retain coherence. The universe absorbs change without losing its character. Scale reveals resilience rather than delicacy. This resilience reshapes how cosmic time feels. Billions of years no longer register as an unfathomable span. They become the natural timescale over which large structures breathe, adjust, and settle. What feels long to human experience feels proportionate to the universe's size. Scale brings perspective by aligning duration with function. Within this alignment, the early universe no longer feels hurried. Its rapid activity now appears appropriate to its density and energy. Things happened quickly because conditions demanded it. As expansion progressed and density fell, the pace naturally slowed. Scale regulates tempo. The universe moves fast when compressed and slow when spread out. Webb captures this regulation by allowing different epochs to be viewed with similar clarity. The early universe does not blur simply because it is distant. It sharpens where conditions allow structure to stand out. Scale reveals not just size, but adaptability across regimes. Another quiet shift emerges here. When the universe is seen as resilient, the unknown feels less threatening. There will always be regions beyond observation, eras beyond reach. But the continuity revealed so far suggests that those unseen regions likely follow the same tendencies. Scale extends trust as well as curiosity. This trust does not close inquiry, it refines it. Questions become more targeted, focused on how details adjust rather than whether the universe behaves at all. Webb's observations suggest that the universe is not withholding its nature at great distances. It is expressing it under different conditions. As this realization settles, the universe begins to feel less like a series of special moments and more like a long, consistent expression. Big events matter, but they do not dominate the story. What matters is how the same physical relationships persist through those events, shaping outcomes again and again. Scale becomes the context in which repetition gains meaning. Each galaxy is unique, yet all galaxies participate in similar processes. Each epoch is distinct, yet all epochs are connected. Scale allows difference without isolation. This balance between sameness and variation gives the universe a recognizable character. It is not chaotic, and it is not rigid. It is flexible within constraint. Webb's images, dense with structure even at early times, reveal this character with clarity. As understanding remains here, the universe no longer feels like something that must be interpreted aggressively. It invites observation that is steady, patient, and responsive. Instruments refine. Models adjust. Insight deepens incrementally. Scale, in this sense, becomes a shared property between cosmos and observer. Both operate through accumulation. Both depend on continuity. Both progress through refinement rather than leaps. The universe continues expanding, carrying its structures forward while gently thinning their density. Light continues its long journey, preserving information even as it stretches. Webb stands quietly in the flow of that journey, receiving signals that have traveled almost the entire history of the cosmos. And with each signal received, scale becomes less abstract and more experiential. It is felt as depth, as endurance, as coherence across time. The universe reveals itself not through singular revelations, but through sustained presence. In that presence, vastness becomes something that can be inhabited intellectually. The universe does not ask to be grasped all at once. It offers itself through layers that can be entered gradually, each one connected to the last. Scale does not end. It continues unfolding, just as the universe does, extending calmly beyond what is currently visible. And understanding follows alongside it, never complete, never lost, always moving forward at the same quiet pace as the light itself. As this long view finally settles, the universe begins to feel complete in a quiet, unforced way. Not complete in the sense that everything has been seen or understood, but complete in the sense that its shape, its behavior, and its rhythm now make sense together. Scale no longer presses outward endlessly. It curves gently back into coherence. The vastness remains. Distances are still immense. Time still stretches far beyond ordinary intuition. Yet none of this feels disorienting anymore. The universe has revealed enough of itself, across enough of its history, to show that its immensity is not chaotic. It is organized, continuous, and patient. What James Webb ultimately gives is not just deeper images or earlier light. It gives reassurance through evidence. It shows that the universe has been structured almost from the beginning, that complexity arose quickly and persisted steadily, and that the same physical story connects the earliest galaxies to the space around us now. Scale, seen this way, becomes less about how small we are, and more about how connected everything is. The light that reaches us today began its journey long before Earth existed, yet it arrives governed by the same laws that shape our present moment. Distance becomes linkage rather than separation. There is a calm recognition here. The universe is not rushing toward an end, nor hiding its beginnings behind impenetrable darkness. It unfolds at a pace set by physics, carrying its history forward in light that travels patiently through expanding space. Understanding follows at that same pace, neither ahead nor behind. Nothing about this picture demands urgency. There will always be more to observe, more to refine, more to understand. But there is no sense of loss in what remains unseen. What is visible already forms a coherent whole, one that stretches smoothly from the first light to now. In this coherence, the universe feels inhabitable intellectually. Its scale does not overwhelm attention. It steadies it. Vastness becomes something that can be held gently without strain, because it is structured rather than arbitrary. The universe continues expanding. Light continues traveling. Structure continues evolving. And quietly, steadily, signals keep arriving, carrying with them the record of everything that has happened so far. James Webb does not end this story. It simply brings it into clearer focus, showing that the universe, at its true scale, is not distant in meaning, not fragmented in time, and not empty at its edges. It is full, continuous, and still unfolding, offering its depth patiently, one signal at a time as it always has.